This is the 23rd video in our series on abstract algebra. In the previous video, we showed that polynomial rings over a field had the division algorithm. In other words, you could take two polynomials and then perform division with remainder. The important thing was the degree of that remainder was less than the degree of whatever you're dividing by. Or perhaps the remainder had degree 0. So today we want to introduce something also that looks like division, the notion of the greatest common divisor. So let's look at our definition. So given f of x and g of x in f adjoin x, where we're taking capital F to be a field, we say a monic polynomial d of x is the greatest common divisor of f of x and g of x if, well, first of all, it has to be a common divisor. So that means d of x divides f of x and d of x divides g of x. That simply means that when you perform that division algorithm, your remainder is 0. Okay, so it has to be a common divisor. And now what about the greatest part there? Well, we'll do our ordering from least to greatest by divisibility here. So that's a partial order, but that works here. So if we have another common divisor, c of x, so c of x divides f and g, then c of x must divide d of x. So that makes like d of x larger than c of x, making it the greatest such common divisor. And then we'll use the standard notation of the letters GCD to mean greatest common divisor. So here we have d of x is equal to the GCD of f and g. Then we use this word monic up here, but I don't think we've defined that yet. So monic means the coefficient of the leading term is equal to 1. So since we're in a field, we can always essentially set the coefficient of the leading term equal to 1 because everything has a multiplicative inverse. So we just multiply that by the multiplicative inverse of that leading term. So monic means this. So d of x has the form x to the n plus dn minus 1, x to the n minus 1, all the way down to our constant term. And then if the GCD is equal to 1, we say that the polynomials are relatively prime, just as we did with integers. Okay, so now we're going to prove something that looks pretty similar to something we call Bezout's lemma in integers, which is about writing the GCD of a polynomial as a combination of those two polynomials. Okay, so let's see it stated precisely. So given f of x and g of x in f adjoin x, we'll set d equal to the GCD. Then there exist a of x and b of x in f adjoin x such that d of x is a of x times f of x plus b of x times g of x. So in other words, the GCD can be written as a combination. And I think like a big takeaway here is if you have a field, then the polynomial ring over that field acts a lot like the integers. Okay, so now that we've got all of this set up, let's look at our proof here. So this proof is very similar to the corresponding proof in the integers. So we're going to consider the following set. And that will be the set of all combinations of f and g like this. So I'll call this u of x times f of x plus v of x times g of x as u of x and v of x range over all f adjoin x. Okay, so something like that. Okay, so now let's take d of x inside of s to be the monic polynomial of minimal degree. So notice the fact that it's a monic polynomial means that it is a non-zero polynomial, so it's not the zero polynomial, because a monic polynomial has to have a leading coefficient of 1. So at smallest, it could be the number 1. And then minimal degree, well, that just means I look at the degree of all of these objects and take the smallest one that's monic. So maybe you might be worried about this word the here instead of maybe the word a, because it's not clear that this GCD is a unique type object. That's something that we'll prove at the end of this theorem though. And I know like it's probably bad form to use the word the here when we have not yet proven that we have uniqueness, but I'm just gonna leave it like that. Okay, so now since d of x is in S, then there's a corresponding polynomial playing the role of u of x and another one playing the role of v of x, putting it in this form. So let's take a of x and b of x to be those polynomials. So in other words, a of x and b of x are an f of x such that d of x is equal to, well, exactly this thing up here, a of x times f of x plus b of x times g of x. I guess another small hole that we didn't talk about yet is that this is a non-empty set. But it's pretty clearly a non-empty set because what we're doing here is ranging over all polynomials, including, for example, the polynomial where u is equal to 1 and v is equal to 0, which puts f of x inside of this set. Or, you know, a number of other polynomials you can put inside of that set as well. So now we've got d of x in the appropriate form, and now we'd like to show that d is in fact a divisor of f. And then very, very similarly, we'll prove that it's divisor of g, but it's so similar that we won't actually do anything for that. So like I said, we're going to look at the following claim, and that is that d of x divides f of x. Okay, so how might we prove this claim? Well, we're going to do the division algorithm with d and f and argue that that remainder has to be 0. Okay, so let's, like I said, do the division algorithm with d and f to produce the following object. We'll have f of x is equal to q of x times d of x plus r of x. And that is where r of x either equals 0 or the degree of r of x is less than the degree of d of x. Okay, nice. So those are the two possibilities for the remainder based off of what we saw last time with the division algorithm for polynomials. Okay, so now what we want to do from here is solve this equation for r of x and see that we'll run into a problem when r of x is not 0. Okay, so let's see. R of x is in fact equal to, so it'll be f of x minus q of x times d of x. But we know that we can write d of x using, let's see, this formula right here. So let's do that. So we'll have a of x, f of x, plus b of x times g of x. Great. But now let's combine like terms. And when I say like terms, I'm thinking about like f of x being a type of term, and then also g of x being a type of term. So let's see. That's going to give us something like this. We'll have 1 minus a of x times q of x times f of x, and then minus q of x times b of x times g of x. Okay, cool. But now let's look at this. If we were to rename these really quickly, we could rename this maybe u of x, and we could rename this v of x. We see that we have something that's in the form of our set S. But since this u and v is ranging over all polynomials, that means that this element is in fact an element from S. But now let's go over here and look at the possibilities of the degree of R. So the degree of R is less than the degree of D, but notice that that's impossible because the degree of D is minimal. So it's impossible to have the degree of R be less than the degree of D since R is inside of S. So that means the possibility that remains is that R of x equals 0. So let's write that here. So this is by the minimality of the degree of, let's see, d of x we know that r of x equals 0, which implies that we have, let's see, right here, f of x equals q of x times d of x, which is exactly what we need to say that d of x divides f of x. And so that finishes the proof of this claim. And like I said, we can very, very similarly prove that d of x divides g of x. It's so similar that we won't even do it. It's just like the symbols are going to be in different places. Okay, so now we have that d is a common divisor of f and g. Now we want to move towards showing that it is the greatest such common divisor. Okay, so far we found this d of x built out of this set. We know that it's of the form a of x, f of x, plus b of x, g of x. We also know that it is a common divisor. So it divides f and g. Now we'd like to show that it's the greatest such common divisor. So looking at this definition over here, that means we need to bring into existence another common divisor and show that that indeed divides d. Okay, so let's bring into existence that other common divisor. So let's suppose that c of x is inside f of x, f adjoin x I should say, such that c of x divides f of x and c of x divides g of x. Okay, nice. But what does that tell us? That tells us that f of x can be written as c of x times p of x, and g of x can be written as c of x times q of x, where p of x and q of x are inside our polynomial ring, so f adjoin x. That's the definition of divisibility here. And now what we'll do is take these two versions of f and g and plug them in to this nice expression up here, which we built on the last chalkboard. So what does that leave us with? So d of x will be equal to, let's see, it'll be a of x times c of x times p of x. That's our a times f term. And then it'll be b of x times c of x times q of x. But the important thing here is we can factor a c of x out. That leaves us with a of x, p of x, plus b of x, q of x. But it actually doesn't really matter at all what's in here. The important thing is that we have d of x equals c of x times some polynomial. So d of x being equal to c of x times some polynomial is exactly the condition to say that c of x divides d of x. So now that, together with these two, tells us that d of x is in fact equal to the GCD of f and g. Well, I guess to be really super careful here, all it means is that d of x is a GCD of f and g. Now we need to show that it's the GCD. And so let's finish that off. So far, we showed that d of x was the GCD of f of x and g of x, but dangerously missing from this argument is that the GCD is unique. So I guess what we've really shown is that d of x is a GCD. But now let's prove that the GCD is actually unique. So let's suppose that something that I'll call maybe d naught is another GCD of f of x and g of x. And since we're going for uniqueness here, we obviously want d of x to be equal to d naught of x. Okay, so since it's a GCD, it's a CD. In other words, it's a common divisor. So that means we can write f as a multiple of d naught and g also as a multiple of d naught. And I'm going to reuse some of my polynomials from before. So let's write f of x as d naught of x times p of x, and we'll also write g of x as d naught of x times q of x. Okay, cool. And now we're going to insert this version of f and this version of g up here, and then I'll skip a step in this case, but we're going to do something essentially like we did before. In fact, we probably could have combined it with the last step, but that's okay. So now we have d of x is equal to d naught of x times, let's see, it'll be a of x times p of x plus b of x times q of x. So again, that's from putting these two equations up here. And now let's take the degree of both sides of this equation. So like I said, we're going to take the degree of both sides of this equation and then use one of the formulas we had for the degree of a product, which is the sum of the degrees. So notice this will give us the degree of d of x is equal to the degree of d naught of x plus the degree of the rest of this stuff. So we have a of x, p of x plus b of x times q of x. So something like that. But let's recall how we produced that GCD, and that was by taking something of minimal degree from a certain set. So that means that this term and this term have the same degree. And that's, like I said, because of how we built them by taking elements of a minimal degree from that set. Okay, but since those have the same degree, well, those two are equal, that tells us that the degree of this object must be equal to 0. You know, just like subtracting one side from the other and just solving for the degree of that. Okay, but if the degree of that is equal to 0, then in fact we know this combination of polynomials right here is equal to a constant. I'll call that constant alpha. Okay, but now we have d of x is equal to alpha times d naught of x. But let's recall that d of x and d naught of x were both monic polynomials. So that means that by extracting the coefficient of the highest term, so I'll just write this, coefficient of the highest term, well, on the left-hand side we'll get 1 because we assumed that d of x was monic. On the right-hand side we'll get alpha times 1 because d naught, being another GCD, is also monic. So we'll get alpha. Oh, but that means that alpha is equal to 1. But now putting that back up here, we see that means that d of x is equal to alpha, which was equal to 1 times d naught of x. So in other words, d of x is equal to d naught of x. And that finishes the proof of this uniqueness. Okay, so now we're going to do some examples of, well, writing GCDs as combinations. Okay, so I haven't written the heading here, but essentially what we're doing is taking two polynomials, calculating their GCD using the Euclidean algorithm, which is that repeated division algorithm, and then afterwards writing their GCD as a combination of them, like the last theorem said was possible. Okay, so we're going to change which field we're working in at each problem. So let's say we'll start in Q adjoin x. Let's take the polynomial f of x to be x squared plus 3x, or plus 2x plus 3. And then we'll take the polynomial g of x to be x squared plus 1. So this is going to be exactly like the extended Euclidean algorithm inside of the integers. It's just we have to keep track of polynomials here. Okay, so let's start by dividing x squared plus 1 into x squared plus 2x plus 3. So notice our starting quotient will be 1 because the degrees are the same. We multiply 1 to x squared, that'll give us an x squared here. 1 to 1 will give us a 1 there. Then we group and we subtract. And down here we'll get 2x, and then let's see, 3 minus 1 is 2. So 2x plus 2. Okay, so what does that really mean? That means we can start off by writing x squared plus 2x plus 3, which is f of x, as x squared plus 1 times 1 plus 2x plus 2. So like that. And now, again, like we would do with the Euclidean algorithm with numbers, we'll take this, and this will play the role of being our new dividend, and we'll take this remainder, and that'll play the role of our new divisor. Okay, so that means we need to divide 2x plus 2 into x squared plus 1. So let's see, in order to get an x squared here, we need to multiply by 1/2. So let's put a half there, and then also an x. So that'll give us an x squared here, and then plus x. And then we need to group and subtract. That'll give us minus x plus 1. But now we can go again. Notice now we'll multiply by negative 1/2. That'll give us a negative x minus 1. Group and subtract. That'll give us a 2. So that means we can rewrite this as, let's see, x squared plus 1 equals, so let's see, this is our new divisor, 2x plus 2, multiplying into 1/2 x minus 1/2, and now our remainder is the number 2. Okay, great. But now notice 2 is simply an element of the field, which means any division we did after this would be like a perfect division with no remainder. Furthermore, since we're supposed to have a monic polynomial, it means that our GCD isn't 2, it's in fact the number 1. But let's get there. Okay, so let's recall that we've got names for some of these. This right here is f of x, and this right here is g of x. So let's invert some of these. So let's invert this one first. Oh yeah, and then let's include this is also g of x. Okay, so that means we have f of x minus g of x is equal to 2x plus 2. So that's how that one inverts. And then from this one, we'll have something also kind of helpful. We'll have g of x minus 2x plus 2 times 1/2 x minus 1/2 equals 2. Okay, great. And now we'll take this version of 2x plus 2 and insert it into the lower equation. And let's see what that'll leave us with. So now we'll have g of x minus f of x minus g of x times 1/2 x minus 1/2 equals 2. But now we can like combine like terms where we're thinking about our f of x and our g of x as being like terms, and that gives us the following expression. We'll have minus 1/2 x plus 1/2 times f of x, and then we'll have plus 1/2 x plus 1/2 times g of x equals 2. Okay, but we want a monic polynomial over there instead of the number 2. So we'll take this whole thing and multiply it by 1/2 to get the number 1 over there. And that'll give us the expression minus 1/4 x plus 1/4 times f of x, and then plus 1/4 x plus 1/4 times g of x equals 1, which, let's recall, that is the GCD of f of x and g of x. So we've done it. We've expressed the GCD, in this case it's 1, so these are relatively prime, as a linear combination of f and g. Okay, so our next example is inside of Z3 adjoin x. We'll take the polynomial f of x, which is x cubed plus 2x squared plus x plus 1, and the polynomial g of x, which is x squared plus x plus 2. So it's going to be the same kind of game. So we need to start with division of a long division of polynomials. So x squared plus x plus 2 is dividing into x cubed plus 2x squared plus x plus 1. Just remember that the only numbers here are 0, 1, and 2 because we're inside of Z3. Okay, so in order to achieve this x cubed, we need to multiply by x to the first power, I guess. That gives us x cubed here plus x squared here, and then plus 2x. Great. Now we group and subtract. So let's see, x cubed minus x cubed is 0. 2x squared minus x squared is x squared. X minus 2x is negative x. But negative x inside of Z3 adjoin x is 2x. So that's plus 2x plus 1. Okay, nice. Where, like I said, I did that calculation inside of Z3. So we have to be careful that we're not inside the rational numbers here. We are inside z3 adjoin x. Okay, so now let's keep going. We need to multiply x squared by 1 to give us x squared. So plus 1 goes here. And then we have x squared plus x plus 2. Now let's group and subtract. So x squared and x squared cancel. 2x minus x is x. And then 1 minus 2 is negative 1. But again, negative 1 inside of z3 is plus 2. So we get that. So that's our remainder. So let's see. That means that we can write f of x. So I'll use this shorthand here. That's this term right here as x plus 1 times g of x plus x plus 2. So there we have like quotient and remainder version of this division that I just did. Okay, now we're going to repeat the process. So now we need to divide g of x by x plus 2. So this is x plus 2 is dividing into x squared plus x plus 2. Because the new dividend is the old divisor and the new divisor is the old remainder. Okay, those were the words. Now, here we clearly need to multiply by x to get us going. That'll give us an x squared here plus 2x here. Group and subtract. Okay, so x squared minus x squared is 0. X minus 2x is negative x. But inside of z3, that is 2x. Now bring down the plus 2. So that means we need to multiply by another 2. So that'll end up giving us 2x plus 2 times 2 is 4. But 4 inside of z3 is 1. So we've got this cancels all the way out. Except we've got 2 minus 1, which is 1. So that's our remainder. So let's see, that means we can write g of x as, let's see, x plus 2 times x plus 2, x plus 2 times x plus 2 plus the number 1. And I'm not going to combine these into an x plus 2 squared because it doesn't really suit our needs here. Okay, so now let's take these and we'll invert each of these to solve for the remainder. So let's see, this first one becomes x plus 2 equals f of x minus x plus 1 times g of x. And the second one becomes 1 equals, let's see, g of x minus x plus 2 times x plus 2. But now we're going to take the above expression for x plus 2 and insert it into maybe this second x plus 2. And that'll leave us with g of x minus x plus 2 times f of x minus x plus 1 times g of x. Great, and now let's gather all of the f of x terms and all of the g of x terms. So notice we'll have minus x plus 2 times f of x. So that's all of the f of x terms. And then for g of x, we'll have plus x plus 1 times x plus 2 plus 1 times g of x. And this is all equal to 1. Okay, so now let's maybe multiply this out to see what we get. So bringing this down, we'll have minus x plus 2 times f of x. So that's from that. And then let's maybe do this little calculation over here, just to put it out of the way. So notice that x plus 1 times x plus 2 will be x squared plus 3x plus 2. But 3x is equal to 0 because we're in z3. So you have x squared plus 2 plus another 1. Oh, but 2 plus 1 is 0. So that's simply x squared. That's kind of interesting. And so all of this condenses to x squared times g of x, and that's equal to 1, which we previously said was the GCD. So there we have our expression of the GCD as a combination of the two original polynomials. All right, let's look at something else. So next I wanted to find the notion of an irreducible polynomial. So we say a non-constant polynomial f of x is irreducible if simply we cannot factor it into polynomials of smaller degree. So in other words, it is impossible to write f of x as p of x times q of x, where the degree of p of x is less than the degree of f of x. But notice if the degree of p is less than the degree of f, then that means the degree of q also would be. Because here we have the sum of these two degrees must equal that degree. So I don't really need to write the other. So it's not really necessary to talk about the degree of both of them. Okay, so now let's look at a little observation which we'll use a lot, but I'll just sketch the proof of. I think it's fairly evident and would be a nice exercise. So if the degree of f of x is 2 or 3, then f of x is irreducible if and only if f of alpha is not equal to 0 for all alpha in f. So in other words, f does not have any zeros within the field. And the idea here is any factorization of a degree 2 or 3 polynomial must include a degree 1 polynomial. That's simply because the only way to get to 2 is with 1 plus 1, and the only way to get to 3 is with 1 plus 2 or 1 plus 1 plus 1. This idea doesn't hold for higher degree polynomials, and that's simply because 4 is equal to 2 plus 2. You could factor a degree 4 polynomial into two irreducible quadratic polynomials, neither of which have zeros. Okay, so anyway, let's get to some examples. So our first example is f of x equals x squared minus 2. So notice this is most definitely irreducible in q adjoin x. And that's simply because the square root of 2 is not rational. Because if we broaden this and look at the real numbers, we know that the roots or the zeros of this polynomial are plus or minus square root of 2, neither of which are rational. That being said, this is reducible in R adjoin x. And that's simply because we can write f of x, which is this x squared minus 2, as x minus the square root of 2, x plus the square root of 2. Okay. Let's also notice that it's reducible in Z7 adjoin x. And that's because in this case, f of x can be written as the following factorization: x plus 3 times x plus 4. Well, let's FOIL this out and see that we get x squared plus 7x plus 12. But 7x inside of Z7 is 0, and 12 is equal to 5, which is the same thing as negative 2. So that's why that works. So it's irreducible in Q adjoin X, reducible in those two other settings. And you can find even more settings where it's both irreducible and some others where it's reducible. The context here really matters. Now let's look at g of x equals x squared plus 1. So this is pretty clearly irreducible in R adjoin x. And that's simply because I, which is the square root of negative 1, is not a real number. It's an imaginary number. It's within the complex numbers. Let's also notice that it is irreducible in Z3 adjoin x. And how do we check that something's irreducible? Well, since it's a degree 2 polynomial, all we have to do is evaluate it at all of the points of Z3 and show that it's never 0, and then apply this observation over here. So let's notice that g of 0 is equal to 1, g of 1 is 1 plus 1, which is 2, and g of 2 is equal to, well, let's see, 2 squared is 4. 4 is 1 inside of Z3, so we get 1 plus 1, which is 2 again. But that's all of the values of Z3, or that's all of the entries of Z3. We never got 0, that means it's irreducible. But notice that it's reducible in a couple of places. It's reducible in C adjoin x because it factors. So x squared plus 1 factors as x minus I times x plus I. It's reducible in Z2 adjoin x because in this case x squared plus 1 factors as x plus 1 quantity squared. Notice the cross term cancels because 2 is equal to 0 here. Furthermore, it is reducible in Z5 adjoin x. And that's because we can write, let's see, x squared plus 1 as x plus 2 times x plus 3. I'll let you multiply that out and convince yourself that inside of Z5 it simplifies to that. Okay, so let's end with a theorem that will set up what we're going to study in the next video, and then I'll give you some warm-ups. So we'll end by showing that if f is a field, then the polynomial ring over that field, f adjoin x, is a principal ideal domain, or a PID. So that means that it must be an integral domain, and every ideal must be a principal ideal. So this is an integral domain for free from previous results. So there we showed that if R is an integral domain, then R adjoin X is an integral domain. Well, every field is an integral domain, so we're good to go there. Okay, so now let's show that every ideal is principal. So let's suppose we have a non-zero ideal. So I guess the zero ideal is kind of obviously principal because it's generated by the number 0. Okay, so 0 is not equal to I, which is inside of F adjoin X, and it's an ideal. Okay, nice. And now we've got to find something inside of I that would be a good choice for its generator. Okay, so what will that be? Well, I think probably a good choice would be the polynomial of minimal degree. So let's take P of X inside of I of minimal degree. So likely there's a ton of polynomials inside of I that have the same smallest degree. And that's because you can change their leading coefficient. You could take the monic one if you wanted to, though. Okay, and so now let's observe that the principal ideal generated by P of X is definitely a subset of I, just by the way these things work. And now let's break this down into cases. So case 1 is like fairly trivial, and that is what happens if the degree of P of X equals 0. Well, if the degree of P of X is equal to 0, that means P of X is equal to alpha, an element of the field. But then it's pretty easy to check that the ideal generated by P of X is simply equal to the whole polynomial ring. That's because alpha is a unit, and whenever an ideal contains a unit, that ideal is everything. Oh, but that means that we've essentially squeezed our given ideal to be the whole field. And that's because our given ideal lives, in between the polynomial ring F adjoin X and our principal ideal. So like I said, we've squeezed that to be the whole polynomial ring. Either way you look at it, it is principal because it's generated by P of X or alpha in that case. Okay, so now let's move on to the second case. And so that second case will be what happens if the degree of P of X is non-zero. So now let's take some sort of arbitrary F of X inside of I and do the division algorithm with F of X and P of X. That'll allow us to write F of X as P of X times Q of X plus R of X, where R of X is 0 or the degree of R of X is less than the degree of P of X. But now we're going to do a trick that we've done from time to time, and that is solve for something and then argue that it must be in some structure. In this case, the ideal. So we can solve R of X equals F of X minus P of X times Q of X. And now let's notice that up here, we took F of X to be inside of the ideal. So this is inside of the ideal. But then this is a multiple of P of X, which means it's in the ideal generated by P of X, which is a subset of I. So that means that's also inside of I. But that tells us that R of X is itself inside of I because it's a combination of things in I. Oh, but let's look at this. We know that R of X is equal to 0 or the degree of R is less than the degree of P. By the minimality of the degree of P, we know that R of X must be equal to 0. So, like I said, by the minimality of degree of P of X, we have R of X is equal to 0. But if R of X is equal to 0, we can just get rid of this right here. And then we have F of X is a multiple of Q of X. But that's exactly what it takes for F of X to be inside of the ideal generated by P of X. But then since f of x was taken to be an arbitrary element of the ideal, that proves that this ideal is in fact a subset of the principal ideal generated by p of x. So now let's see what we have. We have the principal ideal as a subset of I, and I is a subset of the principal ideal, which means they must be the same. So that shows that if we started with an arbitrary ideal, it must be a principal ideal, meaning that every ideal is a principal ideal. Now I'll leave you with some warm-ups. Okay, so I've got 3 warm-up problems based on what we did today. So given the following f of x and g of x, find their greatest common divisor, which we'll call d, and then write d as a combination of f and g, like we did in the examples and like we proved was possible. So let's take f of x to be the polynomial x cubed minus 6x squared plus 14x minus 15, and g of x to be the polynomial x cubed minus 8x squared plus 21x minus 18. And let's do this over 3 different fields. So let's do this in q adjoin x, z3 adjoin x, and z5 adjoin x. Next up, let's find all irreducible polynomials of degree 2 and 3 in z2 adjoin x. So notice z2 only has 2 elements, so it should be pretty easy to write down all possible polynomials and then check if they have zeros using this observation, which in turn checks if they're irreducible. Next up, let's factor x cubed plus x squared plus x plus 1 into irreducible polynomials in 3 settings: z2 adjoin x, z3 adjoin x, and z5 adjoin x. Let's see, to get you started, I'll give a hint of what goes on here. So if we maybe set f of x equal to x cubed plus x squared plus x plus 1, let's notice that f evaluated at 1 is 1 plus 1 plus 1 plus 1, which is 4, which is 0 inside of z2. But that in turn tells us that f of x should be able to be written as x minus 1, which is really the same thing as x plus 1 in z2, times something else. That something else you can find with the division algorithm or long division of polynomials, and then you can repeat the process on that something else. And that's a good place to stop.